All right. Well, let's see here. Okay, you don't want that one. You want this one. All right, can y'all see the acid base indicator page?
Yep.
Yes.
Holy cow, I am so out of breath and I am frozen like a popsicle. Whew. Okay.
Good nice hot cup of cocoa.
You know what? I should drink a cup of cocoa. My hands are shaking too bad right now, though. I'll get one in a while. Okay, so what we need to talk about today is those titrations. And so I'm going to work through an entire titration for you. And then we're going to work on individual pieces. So for the acids and base, we're going to do a strong acid and a strong base. We're going to do weak acids and strong bases, and we're also going to do strong acids and weak bases. Okay, so there's 3 distinct kinds, but 2 of them, the 2 weaks, are almost identical. All right, so here is the generic problem. I'm going to work through it. If you do not want to write everything down, don't feel like you have to, because I have this one completely worked out for you in the handout. All right, but we're going to start with what is happening. During a titration, I'm going to put some sodium hydroxide in the burette, and I'm going to have either a beaker or something, and I will have my weak acid in it. Okay? All right. What's happening is before the titration ever occurs, it's just what is in the beaker. So that is a weak acid going to its, whoops, I should have put HA. Okay, so there's nothing new there. That's just a weak acid. And then we can do all of the equilibrium and we can figure out what the pH is. All right, during the titration, I'm going to be dripping sodium hydroxide into this beaker. It is going to react with my weak acid, and it's going to create, and this should look very familiar, it's just like we did with the buffers. It's going to create water and the conjugate base. Okay, so during or inside the titration, that is the equation that we should be using. And then when we're done, the only thing left floating around in this beaker is going to be A minus plus water. Okay, so it's going to be those 2 and then any counter ions. And they're going to react together to reform some weak acid. Okay, so there are 3 equations that we were always going to use, and we're going to use them over and over. 1, 2, and 3. And if you'll notice, these 2 are always related together. One of them will always be the weak acid equation, and one of them will always be the weak base equation.
I got a question.
Yes.
Well, on C, what does it mean by different species? I don't get what that's supposed to mean.
Oh, that's all of these pieces. What is floating around in your beaker? So right
okay,
now,
gotcha.
I have sodium, I have A minus, I have H2O, and I have some hydroxide.
Okay, thank you.
Okay, I'm going to erase this. Well, it's easier on the whiteboard.
Hey, Jollies.
Yeah.
Are you doing lab today?
I am going to do the lecture. I'm going to put on some snow pants. I'm going to go dig myself out with a real shovel. And then I was hoping that, yes, we need to do lab. We can't miss lab again. So,
If you, I mean. I
We
don't
can
know.
combine it on.
Yeah, we can combine it, whatever. I mean, it might take a while for you to do that.
it's, so there's only, the drift is only, I don't know, a foot, just a little over a foot, but it's like 8 feet wide. And my van is stuck right in the middle of it. And I've dug myself out 4 feet, but I keep backing up into more drift. So,
Yeah.
yeah.
The rest of the roads are not that nice either, so I don't know what the class thinks, but.
Is the next slab extended or?
Oh, yeah. And you know what? That's probably the best thing. We will do maybe a little longer class, do some examples, and then I will do the problems from the lab. And then we will just combine and actually taking those titration readings on Thursday.
Okay.
So longer lecture today and then just lab on Thursday.
I mean, we'll still have lecture on Thursday, but we'll combine everything on Thursday.
Okay.
Was
Okay.
that a longer lecture today?
So
Yes.
just a little bit longer because I'm going to do some problems from lab. So I'm going to help you do lab number 6.
Okay. Thank you, Jolly.
You are so welcome. You guys just put up with me, so you deserve just all the things you want in life.
Aw, you're the best.
Okay, so let's see. So strong acid, strong base. I'm going to go to a clean page here. Okay, so I'm under weak acid and strong base. So number 1, in the titration of 50 mils of vinegar, okay, 0.1 molar vinegar with sodium hydroxide. Okay, the first important thing is to know what is where. So in my burette, I have 0.100 molar sodium hydroxide. In the beaker, I have, let's see, 50 mils of, oh, hold on. Janelle is calling to see what's wrong. So if Janelle shows up to the classroom, you'll know why.
Okay, I'll let her know.
Okay, so I have 50 mils of 0.1 molar vinegar. Okay, so before I start anything, that is what I have set up. So what is my initial pH? Well, the first question is, what am I taking the pH of? The initial pH is inside of that beaker. Well, what is inside that beaker? Inside that beaker is just vinegar. So I have to have an equation. And Ka okay. So it's just like we've done before. And then do I know any of my initial concentrations? Yes. Okay. Hopefully this is not looking new to anybody. All right, I'm going to make the assumption. I'll just check it before I'm done. All right, so I have 1.8 times 10 to the minus fifth times 0.1 and take the square root. And I don't even think I brought my calculator in. So somebody, whoever gets that first, give me the number.
I've got 1.34 times 10 to the negative third.
1.34.
Yeah, times 10 to the negative third.
Excellent. Of course, that's the same one I guess we've been doing over and over. I should have remembered that. All right, let's do a check. Make sure my assumption was valid. And if I remember right, it comes out to be 1.3%. So yes, it's okay to use the assumption. And yes, I can ignore water. So X in this case is the proton concentration. And I'm going to take the negative log of it. And holler when somebody has the negative log.
2.87.
2.87. All right. First off, did we expect an acidic pH? Well, yes, because it was vinegar. Okay. All right. Now we know that sitting inside this beaker, we have 50 mils of vinegar that has a pH of 2.87. All right. How many, going on to B, how many milliliters of sodium hydroxide am I going to need to drop into this beaker to use them all up? Now remember, a titration is when you add equal amounts of acid and base. This one's much easier to erase on. Okay. So a titration see H2O plus A minus. Okay. Well, right now I have 0.100 molar acetic acid, but I want to know how much of this one that I need. Okay, now this has nothing to do with titrations. This is just going back to stoichiometry because the first question is, well, how much vinegar do you have? Well, I have 0.1 molar. Remember, molarity is not a quantity. It is a tool. What I really have is 50 milliliters. And chemists do not use milliliters. Chemists use moles. So I'm going to use my molarity to convert out. And I have
5 times 10 to the negative 3.
-2.
3, negative 3.
Excellent. Thank you. All right. Before I go any further, is everybody following? I'm just converting to moles of what's sitting in the beaker. Good? I guess I can't see a thumbs up. That's really weird.
Yes.
Okay. All right. Well, then that begs the question, how do they react? What is the stoichiometric relationship between them? Now, in this case, it happens to be 1 to 1. It won't always be 1 to 1. So 0.0050 moles of, whoops, I get one more sig fig, of acetic acid. And I know for every 1 mole of acetic acid, I need 1 mole of sodium hydroxide. Okay, so I'm out of moles of acetic acid and then I'm in moles of hydroxide. So in this case, it happens to be the same number. But it asked what volume, and so that begs the question, well, what concentration do I have? Because I know that there's 0.100 moles in every 1 liter, and then I'll go to milliliters. Oh, look. In this case, because it was 1 to 1, and they had the same concentrations, I need the exact same milliliters. Okay? Anybody have a question on that?
No.
Okay. All right. So now we know our initial pH is 2.87. We know that we need 50 mils of our 0.1 molar sodium hydroxide solution to be done. All right. What is our next question? In fact, sorry, you're probably going to get sick me going back and forth between these all the time. Okay. So we did how many milliliters of sodium hydroxide? Ooh, I'm going to hold off on this one. Okay, I'm going to hold off on C. What is the pH when 30 mils have been added? What is the pH when 30 mils has been added? So let's go back to the whiteboard. Okay, that begs the question. Am I before the titration started? Am I during the titration? Or am I when the titration is done?
During?
I am during. So what equation should I be using? It's this one. Okay. All right. Now, in this case, we are going to create a buffer. So I'm going to be in moles, and I'll show you what I mean. Normally right here, you would plug in molarities. You would do a dilution, and then you'd plug in molarities. But I'm going to plug in how many moles I have. Oops, too many. All right, sodium hydroxide. I added 40 mils. All right, so that should be 0.00400 moles, and I did not start with any acetate. Okay. Do I have enough acid to sop up all that base? And the answer is yes. So I'm going to use it all up. And I have 0.00100 left. But the beauty is, guess what? Anytime I start a titration, I am buffered through the whole thing because I always make the conjugate piece. So inside of a titration, we can use the Henderson-Hasselbalch and we can be in moles rather than doing all of the dilutions, Oh, nifty. So the pH is equal to the pKa, which is 4.74, plus the log, and this doesn't change. It's always the base piece over the acid piece. And the log of it. All right, I got a 5.34. Is there a confirm?
Confirm.
Okay. Did I expect a pH of 5.34? Now, remember, I am not comparing to this. That is not my initial pH. My initial pH was 2.87, and now it's 5.34. It is less acidic because I added base in. So yes, I should expect the pH to be going up, but it is buffered, so it's not jumping by huge quantities. Okay. All right. Our next one, let's do, okay, I'm going to do just a few more than what I had on the board. or on that paper, I'm going to do the pH at 49 milliliters. Okay, the pH at 49 milliliters. All right. I originally started with 0.00500 moles of my acetic acid. At 49 milliliters, I have added 0.00490 moles of my hydroxide. Remember, at the beginning, there is no acetate. Do I have enough acid to sop up all this base? And in this case, the answer is yes, barely. Somebody check my math on that. Is 3 zeros, okay. Okay. Am I still buffered? Yes, I am. So I can use the Henderson-Hasselbalch. So the pH is 4.74 plus the log of 0.00490 divided by 3 zeros, 10.
I have 6.43.
6.43. Excellent. Confirm on anybody?
Confirm.
Excellent. Okay. It's still slowly going up. It's still slowly going up, which we expected. All right. Now, what should happen when I hit the equivalence point? Okay, so equivalence point and endpoint mean the same thing. Equivalent just means there's the same number of moles, and end means when you're done. Okay, so either of those two, equivalence or endpoint. Well, where is that? Well, I started with 0.0050 moles of acetic acid, so the endpoint is going to be when I add the exact same amount of base. And we know that's going to be 50 mils.
Is that only the case when it's a 1-to-1 ratio?
Yes, that is only the case. Now we're going to be doing a lot of one-to-ones, but that is true for one-to-one relationships. All right, so I can look at these numbers and I can tell that I must be done because, oh, do I have enough acid to sop up all that base? And the answer is I have exactly enough. I can mute you when I have to cough. That's kind of cool. Okay, so am I still buffered? And the answer is no. Okay, what do I have floating around now in my beaker? Okay, so literally at this moment, what is floating around in the beaker? I have some water that I made, I have some acetate that I made, and I have the sodium ions that came from the sodium hydroxide. Well, is the acetate going to do anything in the presence of that water? And the answer is yes. So we are to our third equation. So when we're done, the acetate is going to react with the water to make a little bit of acetic acid and some hydroxide. These are not the original ones. Okay, I have used up all of the original acetic acid and I've used up all the sodium hydroxide that I put in. These two came from the acetate reacting with the water. Okay, well, how much acetate do I have? I didn't start with any of those. Oh, look, this is just a weak base problem. This is just a weak base problem. Oh, it's a weak base problem, so I can't be in moles. I have to be in molarity. And so right now I had 50 mils plus 50 mils, so 0.100 liters. And if somebody will plug that out for me, what is that new concentration? So 0.005 divided by 0.1
0.05.
is a 0.05. Okay. Okay, I'm back in molarity. 0, 0, minus x, x, and x. 0.050 minus x, x, and x. And we're back to everything that we kept doing over and over. Now remember, this is a KB. So where do I find the KB? You can look on the sheet, but normally you have to use the KA. So the KW divided by the KA equals the KB. And that number is 1 times 10 to the minus 14th divided by 1.8 times 10 to the minus 5th and 5.6 times 10 to the minus 10th. Somebody confirm on that, please.
Yep.
Excellent. All right. I have my KB and now I'm going to plug everything in. All right, so 5.6 times 10 to the minus 10th is equal to x squared over 0.050 minus x. I'm going to ignore the x. All right, somebody plug and chug. What does my x turn out to be?
I've got 5.27 times 10 to the negative 6.
Excellent. Did I hear that right?
Yeah.
Okay, confirm.
Confirm.
Excellent. Okay, but I can't use this number if I don't check it. So I'm going to divide it by 0.05, multiply it by 100, and guess what? It is very valid. And I'm just barely squeaking by being able to ignore water. Okay, so this number is okay. Okay, well, what is X? X, in this case, is the hydroxide. So my hydroxide concentration is 5.3 times 10 to the minus 6. When you're writing it out of X and as concentration, make sure you put your molarity and then take the negative log. So the POH is
Also just 5.3.
wow, the POH turns out to be 5.3 as well.
Yes,
Well, that's kind of tricky. All right, and then 14 minus that.
that's 8.7.
Did we expect it to get out of the acid range and up into the basic range? Yes, because we've used all of our weak acid and the only thing floating around now is weak base. So we've got from 2.87, then 5.34, and then 6.43, and now we're up at 8.7. Well, what happens if I put too much in? Okay, we call that an overshoot. What if I put an extra milliliter in it? So I need only 50 milliliters, but let's say I accidentally, put 51 milliliters in it. That's okay. We can do the exact same problem. And the beauty of it is the math will always work out for us. Even if we don't know where we are, the math will say, hey, guess what? You're right here. All right, so the new question is, what will the pH be when I've added 51 milliliters of my sodium hydroxide? Well, that would be 0.00510 moles. Do I have enough acid to sop up that base? And the answer is no, there's too much. So this time I'm going to use up all of my acid. And I'm going to be left with 3010 moles of my strong. Remember, this is the strongy that I added. And I'm going to create 0.005 moles of my acetate. But who is controlling the pH right now? Is it my strong excess base? Or is it my poor little weak base that I created? Now, technically, I should find them both and add them together. But this is going to be, we just did it. It's 5.3 times 10 to the minus 6th. Okay, so remember that. We just did that one. And it turned out to be 5.3 times 10 to the minus 6th. All right, well, what in the world is going to happen here? This is how many moles of excess I have. You can't take the negative log of a mole, so we need to convert that back out to molarity. And so I have 0.12310 moles, and I had 50 mils originally, and I added 51. So I have 101 milliliters right now. And then somebody plug and chug. What is that new molarity?
It's 9.9 times 10 to the negative 6.
Excellent. Thank you. Confirm.
9.9.
Oh, 9.9. Perfect. Okay, now remember, this is excess strong sodium hydroxide. There's no equilibrium for the strongies. We're just going to take the negative log of it.
I've got just 5.
Ooh, okay. So the pH, sorry, that's the pOH. So the pH is going to be 9.
Yeah.
Well, what if I overshot by 5 milliliters? Okay, I would just have a bigger number right there. Okay, before I erase everything on this page, we're going to do a little graph. See what in the world is going on. On the Y, I'm going to put the pH. On the X, I'm going to put the volume. So this will be 0, 1, 2, 3. Okay, and then we'll do 10, 20, 30, 40, 50, and 60. All right, before I added anything, I had a pH of 2.87. So 2.87. Then when I added 40 milliliters, I had 5.34. So 40 milliliters was 5.34. At 49 milliliters, it was 6.43. And at the halfway point, Good grief, Jolly. I'm gonna have to draw my graph better. This is giving me flashbacks to college algebra. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. And we'll go 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, and 65. All right, let's do this again. All right, at 0, it was 2.87. At 40, it was 5.34. At 49, it was 6.43. At 50, it jumped all the way up to 8.7. And then at 51, it was clear up at 9. All right, now that's not very many points, but the graph is looking like this. And then if you overshoot, it will keep going. All right, this initial spot right here, my initial pH, okay, that's just what's in the beaker. Right here, okay, this little spot right there, the moment I add any type of hydroxide to it, I am buffered. So from here to here, I am buffered and I can use the Henderson-Hasselbalch. So it shouldn't change really drastically. Okay, so the buffer should change the pH slowly. Now there's not enough points on this graph to really look at that, but it's not increasing too fast. Oh, right here, I'm done. So this is the end point. And then after that, it's just going to jump up into the excess region. Okay, so that is exactly what I just did. All right, let's ask ourselves. We're at 51 milliliters. What is floating around in my beaker? Okay, so I had my original 50. I have 51 of my sodium hydroxide. So right now I have 101 milliliters. And what's floating around in there was sodium and hydroxide from the excess, the AC and the water that was made, and then those two will react together from that weak base. So what species are present at this moment? There's the acetate, there's some water. The acetate and the water reacted together to make some vinegar and some hydroxide. And this came from my overshoot. Okay, and there's lots of sodium ions floating around in there. All right, you're either going, oh yeah, that makes sense, or whew, too fast. Okay, we're going to do a complete one, and we'll just change the identity. Instead of acetic acid, we'll do lactic acid. We'll do lactic acid. Does everybody have everything written that they want?
Yeah.
Okay, so I'm going to clear this.
Is the process the same for a weak base and strong acid?
Yes, except you start with the
Flip it around.
KB and then you end with a KA. Yes, it is
So it's just-
exactly
Flipped around, basically.
correct. All right, we are going to start with some lactic acid. How much? Let's do 25 mils of 0.200 molar. And, okay, what should I add to this to use up all of my acid? This is a weak acid, so I'm going to add a strong base. All right, what bottle are you going to grab off the shelf? So I'm going to make them different this time. So I have a bottle of 0.15 molar sitting on the shelf, so that's the one I'll grab. So right now, in my burette, I have 0.150 molar sodium hydroxide. And in my beaker, I have 25 mils of 0.2 molar lactic acid. All right. And we can do those steps in any order, okay? You don't have to go A, B, C, D. They can be done in any order. I just tend to, go in a specific order. All right, first question. What equations am I going to use during this titration? So before the titration begins, it's just lactic acid. Whoa, that's supposed to be a C. Okay. During or inside, my lactic acid is going to react with the hydroxide to make water and some conjugate base. When I'm done, that lactic base will react with water to create a little bit more of my weak acid and some hydroxides. Okay, so before I do anything, I know that those are the three equations that I'm going to use during this titration. All right, are there any questions how I came up with those equations? Okay. All right, so there's the first step down. All right. Number 2, I'd really like to know how much sodium hydroxide that I need. I always like to find that out at the beginning so I know where I'm at in that titration. All right, hey math, if I have, oh, I'll tell you, that's pretty nifty that I can mute you and cough. All right, so hey math, if I have 25 mils of 0.2 molar lactic acid, how much sodium hydroxide do I need? Well, chemists don't compare volumes of things, we compare moles. So that begs the question, how much lactic acid do you have? Well, let's find out. Can't be in milliliters. And in this case, my molarity is 0.2. All right, somebody plug and chug.
I have 5 times 10 to the negative third.
Sorry, does somebody have it?
5 times 10 to the negative third.
Let me see, and how many sig figs do I get? So 5.00 times 10 to the minus 3 moles.
Jolly, I have a question.
Yes, please.
So is it, it's 1-to-1 because you only need like 1 OH per each lactic acid, right?
Correct. In
So
this
if it was
case,
polyprotic, then we would need more than one and it would be 1-to-1.
correct. That is correct.
Thank you.
All right. That's how much lactic acid I have. Okay, so I'm going to put a little note to myself up here. This is 0.0 0.00500 moles. How much of the sodium hydroxide do I need? Well, in this case, it's a 1-to-1. I hope you're having visions back to Chem 111. And when I said, it's all about the dimensional analysis, this is where it really comes into play. For every 1 mole of lactic acid, I need 1 mole of hydroxide. So I need the same number of moles of the sodium hydroxide. Okay, but this is where it's different. So I still need 0.00500 moles, but it has a different concentration. So how many milliliters is that? So let's use our molarity. I know that there's 0.150 moles in every 1 liter. And holler when somebody has it.
Was that all? Then it'd be 3.3 times 10 to the -2nd.
Okay, confirm on that. Did anybody else get the 3.3?
We're being slow.
No worries.
Confirm.
Okay. Now, that's in liters. I don't want to be in liters. I want to be in milliliters. So I'm going to convert that out. And so I have 33.0 milliliters. Okay, so if you'll notice, I need the same number of moles, but I don't need the same volume because it is not the same molarity. Okay, that's very important to distinguish. Yes, I need the exact same number of moles, but I might have to use a different volume to get it. Okay, so that's a huge thing. I know I'm making a big deal about that, and you're like, yeah, but it'll come up later, and you'll go, well, how come they're not the same? Okay, so what do I know? We haven't even started the titration yet. I know that I have 0.005 moles of my lactic acid. I know that I need 0.005 moles of my sodium hydroxide, which in this case is going to be 33 milliliters. And what will be my next question? You know what? What's going to be floating around when I'm done? Let's ask that question. What's going to be floating around? What are my species at the end point? All right. So which equation am I at right now? Now, I didn't overshoot, so I'm using this equation. So these two, that's what was created. And when they're together, they will create these. And then don't forget counter ions. So right now, I should have some lactate, some water, some weak acid, and some hydroxide. And then don't forget the counter ion is just floating around. So when I am done, that is what should be in the beaker. This is not the original. Okay. That is not the original lactic acid, and that is not the original sodium hydroxide. I created that. All right. So I have my equations. I know how much I need. All right. Let's just start. What is my initial pH? All right. Which equation should I be using? For an initial pH, have I added anything into that beaker yet? And the answer is no, I just have weak acid. So, and I'm going to erase this so I have more room. Okay. What is in my beaker right now? Well, I've got some lactic acid. And it will ionize into protons and lactate. My Ka, oh, where's my reference sheet? The Ka for lactic acid is 1.3 times 10 to the minus fourth. Somebody confirm that.
Yes.
Excellent. All right. How much lactic acid did you start with? Okay. Now, yes, I have 25 milliliters, but before I've added anything, who cares? Okay. So I'm just going to put the molarity because it's all the same molarity right now. I didn't start with any of those. Minus X, 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 and 0.2. When you are completely sick of me setting these up, you really have it down. I'm going to ignore X. And somebody plug and chug.
5.1 times 10 to the negative third.
Okay. Can we trust it? I'm going to divide by my original times 100. And I'm going to go out on a limb and say, yes, this one's going to be less than 5%.
Yep, it's 2.5%.
2.5. So yes, it's less than. And it's greater than 10 to the negative 6. So both of my assumptions are okay. So 5.1 times 10 to the minus 3 molar. And I want the pH, so take the negative log of that.
.29.
2.29. Did we expect an acidic pH? Well, yes, because right now it's lactic acid. All right, any questions or thoughts before I go to the next one? All right, we are going to, let's do a few more. Let's go 10 milliliters, 10, 20. Yeah, we'll just work our way up so that we have a few points for a graph. So let's do the pH when 10 milliliters. Whoops, that's a 10. What is the pH when 10 milliliters? Okay, now that begs the question, which equation should I use? What's going on after I add? So it's not this one. I need to be using my lactic acid. We'll try and sop up all of the sodium hydroxide that I drip in, and it will make water plus lactate. Okay, well, can I get numbers from this? Well, that begs the question, how much lactic acid did you start with? Now I have a choice right here. I can either figure out what the dilution is, but I know during titrations I'm buffered, so I'm going to go straight to moles. And I had 0.00500 moles. Make a little note to myself that these are moles. And so how many moles are in my 10 milliliters of the sodium hydroxide? So the 10 milliliters. Is it 0.00150?
Yes.
Okay, so that's how many moles that I have added. And I didn't start with any lactate. Do I have enough HLAC to sop up all of my base? And the answer is yes. 0.00150. Gonna use up all of that base I put in, and I'm going to create some lactate. And somebody plug and chug.
It's 3.5 times 10 to the negative third. So 2 zeros.
2 zeros. Yep. Okay. All right. Now I either need to use the equilibrium expression or am I buffered?
You're buffered.
And the answer is yes. Hallelujah. Because other words, we'd have to do all those dilutions. So the pH is equal to, whoops, I don't know the pKa yet. So take the pKa or take the Ka of lactic acid and take the negative log of it.
I've got 3.89.
Excellent. Plus the log of the base piece divided by the acid piece. All right, plug and chug.
pH is 3.52.
All right. Should we still be acidic? Yes, there is still lactic acid floating around. Did I expect it to go up by that far? Okay, relatively. It is buffered. So remember, I started at 2.29. I am now at 3.52. The most common error I made when I was in your shoes is I would say, ooh, I'm 3.52 and I started at 3.89. That's not true. That's the pKa. The pH I started at was 2.29. And so I have gone up to a 3.52. Oh, okay. I expected that because I threw some sodium hydroxide in there. I used up some of my lactic acid. Well, how about, let me see. Let's do, what's half of, you know what, let's just do 15. What is the pH when I've added 15 milliliters? Okay, now I'm hoping this is going to get boring very quickly. Oh, I started with 0.00500 and 0. How many moles are in 15 milliliters? Convert out of milliliters into liters, and it's 0.150 moles.
But 2.25 times 10 to the negative third.
2.25. Excellent. All right. Do I have enough acid to sop up all that base? And the answer is yes. So anywhere inside the titration, that's going to be the question. All right. And what would be the lactic acid?
That's 2.75 times 10 to the negative third.
Excellent. Am I still buffered?
Yep.
Yes. So we can still use the Henderson-Hasselbalch. And base piece. All right. And now what is my new pH?
3.80.
And if you'll notice, that's not a huge jump. Okay, there's always a big initial jump because I wasn't buffered and now I am. So there's usually a big initial jump, but now the pH is, or the buffer is working because my pH isn't changing by very much. All right. There is something called the halfway point or the half equivalence point. That's where I put half enough in. All right, well, that begs the question, what is half of 0.005 moles? Well, it would be 0.0025 moles. All right, is everybody seeing where I got that number from? So it's exactly half of what I need. So that's called the halfway point. And
Just 3.89.
yes, thank you. Yes, because there's something very special at the halfway point. The pH is the same as the pKa. So do I have enough acid to sop up all that base? Why, yes, I do. But as a consequence, I'm going to make the same amount of conjugate base. Oh, look, I am buffered. And at the halfway point, they're equal. So the pH is equal to 3.89 plus the log. The log of 1 goes away. So at the halfway point, the pH is always the pKa for weak acid and weak base titrations. All right, and how many milliliters did that take? Well, whatever half of 33 is. All right, before I go on, is everybody still following? Okay, all right. Let's just get a couple more points so that we can graph this when we're done. Let's do the pH at 20 milliliters. Okay. Well, my lactic acid is still going to sop up my base. And I started with 0.00500 moles. And at 20 mils, all right, can somebody calculate that without me drawing the whole thing out?
It's
Convert.
0.003.
Thank you. All right, do I have enough acid to sop up all my base? Yes. Oh, look, I'm still buffered, but I knew that because I've added 20 when I know I have to put in 33. So my pH is, somebody plug a jug.
4.07.
Yeah, my little buffer is doing pretty good. It's not changing by much. All right, let's do the pH at 30 milliliters and then at the end point. All right, at 30 milliliters, how many moles have we added?
0.0045.
Did I hear that correctly?
Yes.
Okay. Do I have enough acid to sop up all that base? Yes. Whoa, I can do that math in my head, although somebody's still gonna check it.
That's right.
Okay. Okay, that acid piece is getting pretty small, so it's gonna start changing more rapidly. And my new pH is
4.84.
woohoo. Okay, let's do the pH at the end point, which in this case happens to be 33 milliliters. All right, do I have enough acid to sop up all of that base? And the answer is yes, I have exactly enough. And if you ever say yes, you have exactly enough, that means you're at the end point and you're not supposed to be using this equation anymore. Because what is the only thing floating around in your solution? Right now, the lactate. So what's going to happen when the lactate reacts with the water next to it? Okay, I'm now at my third equation. And 0.00500 moles. Oh, this is a KB, and KBs cannot be in moles. We have to be in molarity. So right now, how many milliliters do I have? My original 25, and I've added 33.
58.
So 0.058 liters. And what is that molarity?
0.086.
Excellent. All right, this has nothing to do with the titration anymore. This is just weak base. Did I start with any of those? No. So minus x plus x plus x. And my KB is going to be the KW over the KA. And so somebody chug that one out.
I've got 7.69 times 10 to the negative 11.
Okay. So 7.7 times 10 to the minus 11th is equal to x squared over 0.086 minus x. I'm going to ignore the x. All right, so 7.7 times 10 to the minus 11th times 0.086 and take the square root.
2.58 times 10 to the negative 6.
Let's check it. 0.086 times 100, and guess what? This is a very valid. And I'm just barely squeaking by on ignoring water. But I'm still okay on both of those. So my molarity of my hydroxide is 2.6 times 10 to the minus 6th molar, and take the negative log of that, and the POH is,
5.59.
and the pH is,
8.41.
did we expect to have a basic pH? Well, yes, because weak base is now floating around in my water. All right, now in order to get a graph, we need a couple of overshoots. So let's do 5 milliliters and 10 milliliters of an overshoot. Alright, so what is the pH at? Let me see, 5 would be 38 mils. So I still start at a 0.05, oops, 2 zeros, 00. And 38 milliliters is how many moles of sodium hydroxide?
0.0057.
Do I have enough acid to sop up all that base? No. So I'm going to use all my acid. Am I buffered? No.
Oh, man.
Okay, that is telling me I have excess strong base floating around. So I could find the hydroxides from the weak and I could add them to the hydroxides from the strong, but we've done it many times and the weak is always negligible. So who's controlling the pH? It's the strong. But guess what? In order to take the pH or the POH, I have to have a molarity. And so what volume am I sitting at right now? Let's see, I had my original 25 and now I added 38. So I have 63. So my new molarity is
1.11 times 10 to the -5th.
and take the negative log of that.
I've got 4.95.
And I remember taking the negative log of a hydroxide is a POH. And so the pH is 14 minus that.
Which is 9.05.
And if I add 10 more mils on top of that, so the pH at 48 would be, oh well, let's just do it. All right, I started with 0.0050. How many moles of hydroxide did I throw in when it was 48?
0.0072.
Do I have enough acid? No. Oh, not buffered. Who's controlling the pH? My strongy. And I can just take the negative log of the strongy as long as it's in molarity. My original 25 plus 48. 73 this time. And that new molarity is,
I'm working on it.
come on,
Working on it. I've got 0.003.
0.003. And take the negative log.
Got 1.52. I must have done the earlier one wrong. I might have done the 38 one wrong.
Oh, because it really jumped this time.
Yeah, I did it wrong, I think. Because I've got 1.52.
And then the pH would be,
Is 12.48.
And I'm getting sloppy. I haven't been asking for confirms, so we will double check that 9.051. But it could be right. Okay, whew. Let's make a graph. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And let me see. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50.
So a couple of those. Times the-
All right.
times
My initial pH when no sodium hydroxide was added was 2.29. So 2.29. At 10 milliliters, it was 3.52. Okay, now notice there's an initial sharp jump. Okay, the minute you add any, you're gonna have that first sharp jump because it wasn't buffered to start with. And then 3.80. And then the halfway point, which is about right here, is 3.8. Wow, my scaling really stinks, but you get the idea. 3.89, and then 4.07. Where's that? 20 milliliters. At 30 milliliters, it's 4.84. And at 33 milliliters, it jumps all the way up to 8.41. At 38 milliliters, it's 9.05. And then a big overshoot, it's clear up in the 12s.
We
All right.
might have, we might
Yeah, we
have
might have done
had
33 and 38 wrong.
wrong 33, but we know that it will increase, right? So.
Yeah. The shape should be the same, but we might have gotten the numbers wrong.
I'm trying to remember how much. Let me see. We had 0.00. Yeah, I mean, but it's close.
I don't remember, I'm sorry.
Okay. No, no worries. If it had been a really weird number, I would have jumped on it. Okay. All right. So my graph pretty much looks like that. Okay. If you go to the two steepest areas and halfway in between, okay, that is your end point. Right here is your initial. N-I-T-I-A-L. Okay, guess what? This is the pretty cool thing. At the halfway point, so it looks like it took about 33 mils, so 15, 16. This is the halfway point. And if you go back, so where does that look? 4.0. So the pH at the half point roughly, okay, now this is from a graph, so it looks really ugly, is 4.0. But I know the pH equals the pKa at the half point. So my Ka is a negative 4.0, or sorry, 10 to the negative 4.0. So I could actually find a potential ballpark of my Ka. Okay, that's the power of a graph. That's the power of a graph. Whew. And right now, you are tired of writing, and you're definitely tired of watching me put all these numbers on the board. Are there any specific questions on any of the parts? Okay. All right. Let me show you a weak base. We'll just use ammonia. And we will take 25 mils of a 0.1 molar ammonia. And what would you add to a base? You'd add an acid, a strong acid. Which one? I don't care. HCl, HBr. Okay, I'll just say HCl. And again, I'll make it different. Nope. You know what? I'm going to make it the same. So this time, my HCl is in my burette. And my ammonia is in my beaker. Okay. All right. What 3 equations will I be using? Well, before the titration begins, it's just ammonia, which will react with water to make ammonium plus hydroxide. During, I will be dripping in strong acid, and the ammonia will react with it to make ammonium. And when I am done, my ammonium will react with the water to go back to ammonia and a proton. All right, so before I even start, those are the equations that I know I'm going to be using. All right, let's jump in. Oh, you know what? It's always nice to know how many moles am I starting with and how many moles and milliliters of the titrant. Okay, so this is the titrant. Do I need? So let's just ask ourselves that first. All right, how many moles of the ammonia do I have? So 25. Get out of milliliters. And is it 2 zeros? 0.00250? Okay. Now, right now, I can tell you I also need 0.00250 moles of my strong acid. Okay, because to reach the endpoint, they have to be the same. But what volume of the HCl do I need? In this case, because the concentrations are the same, I will also need 25 mils of it. Okay. I at least now know how much that I need to add to be done. All right. So my first addition, I got a little crazy and I added 28 mils. Where am I at? What's going on right now? What would we call this? Okay, that's an overshoot. Oops. Okay. So I was trying to do this. And 0.00250 and 0.00280. Oh, do I have enough base to sop up all that acid? Oops, no. So I'm going to use up all my base. And I'm going to have some excess strong acid. Okay, I am not buffered. Don't care about the weak. Okay, yes, it will donate some protons, but not very many. This is excess. But I can't take the negative log of a mole, so I'm going to convert it back to molarity. And right now I had my original 25 and I added 28. So my new molarity of my excess acid is
About 1.59 times 10 to the negative fifth.
Excellent. Take the negative log of that.
I've got 4.70. I've got 4.80.
Okay. Let me see, that was at 28. All right. Oops. So I used all my ammonia and I overshot, okay, into the 4.8 region. All right. Well, what's my initial pH? Okay. What would be the initial pH in there? What equation should I be using? All right. So if I'm initial, there's only ammonia floating around with that water to make ammonium and hydroxide. Well, how much? Okay, now in this case, I don't need to be in moles because there's only ammonia floating around. So I can use the molarity because I haven't diluted it. 0, 0, minus x, x, and x. And the KB, you can actually look this one up. It is 5.6 times 10 to the, nope,
That's 1.8
1.8.
to the negative fifth.
X squared over 0.100 minus x. Ignore the x. The x should come out to be 1.3 times 10 to the minus fifth, I believe. Somebody check that.
I've got negative 3.
Negative 3, thank you. Okay, let's do our checks. 1.3%. So that one's okay, and it's greater than 10 to the minus 6, so that's okay. So I'm going to put that number up here, 1.3 times 10 to the minus third molarity, and take the negative log of it.
2.87.
Sorry, one more time.
2.87.
2.87, thank you. And the pH?
11.12.
All right. Whoa, I started with a pH of 11.12, and then I jumped to a pH of 4.80. Well, yeah, because I used all of my ammonia, and the only thing floating around now is extra acid. Okay, what is the pH at the halfway point? Okay, trick question yet not trick question. What do we know about the halfway point?
The pH is equal to the pK.
The pH is the same as the pKa.
Yeah. So that.
So the pH at the halfway point, the pK, now remember, it's the pKa. So how are we going to find the pKa? Well, I know the Kb is 1.8 times 10 to the minus fifth. So the Ka is 5.6 times 10 to the minus 10th. So the pKa, I think it's 9.25.
Yeah, 9.26.
9.26. Aha, I didn't even have to do any of the problems. Because at the halfway point of a weak, either acid or base titration, the pH will be the same as the pKa. Let's do the pH at the end point. Well, that begs the question, what is the end point? It's when I put the same number of moles in. So what equation should I be using? I should be using my final one. Okay, so I'm going to write it during, but it's going to show us that I should be using the final one. So NH3 plus that acid is making my NH4, and there's 0.00250, but I've added 0.00250. So I'm going to use up all of those, and I'm going to make some ammonium. And if you'll notice, the table is telling us, what are you using this equation for? The only thing floating around is weak acid. Okay. Oh, okay. Well, I guess I should be using this equation. But you're not allowed to plug moles into a weak acid equilibrium. So I have 0.00250 moles. Okay, but what volume am I sitting at right now? It took 25 mils of my original and 25 mils of what I added. So I have 0.05 liters. And so what does that turn my molarity to be?
Got 0.05. That's kind of confusing. I guess that makes sense.
Oh, yeah, that makes sense because I doubled the volume. So we halved the concentration. Minus X, X, X. And hopefully this part is getting very old to you. Make the assumption and plug and chug X.
Got 5.29 times 10 to the negative 6.
Okay, gonna double check. Yes, it's less than 5%. Still over -6, so those are okay. And so X in this case is the proton. So take the negative log of it
5.28.
and 5.28. Did we expect the pH at the end point to be acidic? Well, yes, because the only thing left now is weak acid. Okay, and then we could also do an overshoot. We could do an overshoot. But do you see that these can be done in any order? Okay, it can be done in any order. You just have to know, where am I at for that particular question? And just to do a compare and contrast, let's draw what that graph would look like. So 5, 10, 15, 20, 25, and 30. All right, my initial pH was 11.12. my pH at 28 was 4.80. My pH at the halfway point was 9.26. And my pH at the end point was 5.28. Okay, now that's not very many data points, but I have an initial drop and then, okay, completely ugly. If I had more points, it would look like that. Okay, I don't have very many points though. All right. That would be a weak base with a strong acid. All right, I'm gonna,
It's like the weak acid, strong base, but like flipped vertically.
yes. You just start at a basic pH and end up at a acidic pH.
Okay.
All right. Let's talk about those indicators. So if this is a weak acid and a strong base, you're going to start somewhere down here and you're going to end somewhere up there. If this is a weak base, strong acid, you're going to start up here and you're going to end down there. And the one I haven't shown you yet is a strong acid with a strong base, and it goes, it's a perfect S. Okay, there's no buffer. Okay. Just as a rule of thumb, okay, just as a rule of thumb, 2 or above, okay, a pH of 2 or above, we're going to consider weak. So if you look at a graph and it starts at a pH of 2 or above, oh, that must be a weak acid. If it is a pH of less than 2, we're going to consider that you started with a strongy. So for instance, if you started at a pH of 1. On the flip side, if you have a pH of greater than or equal to, let me see, 13, okay, that would be considered strong. And if you have a pH of less than 13, that would be considered a weak base. So if this started at 10, okay, that would be considered a weak base. Okay, that's just a rule of thumb. Just as a, hey, did you start with somebody strong or did you start with somebody weak? Okay, those are your generic rules. All right, where is the end point on each graph? When you have the graph, you go to the 2 steepest slopes and you go halfway in between. That is your end point. Halfway is also the Ka. Okay, so that's a very important point on a graph for a week because I could get the Ka and then this is my initial. I could always work backwards, my math with initial, and anything up here is an overshoot. All right, so that's what my graph looks like. But my question was, what indicator, okay? It needs to change, okay? If I start with a weak acid, if you'll notice, it's changing in the weak base pHs. So my indicator, it can't turn colors until I'm clear up here in these weak base numbers, basically greater than 7. So what indicator would we use? Well, I don't know. Let's go look at our pKa chart. And I'm looking at, oh, it's not in the reference. I'm going to go back to the notes. Share. Where are your notes? Okay, there we are. All right. In the notes. All right, here's my choices. I mean, we have lots of choices in the lab, but I'm going to give you these 3. Methyl red it will turn colors in a pH of 5. Bromothymol blue will turn at exactly 7, and phenolphthalein will turn at 9. Okay, this one's too early. Okay, so for that weak acid titration, I don't want it changing colors in the acid range because I won't be done and my indicator will have changed. The 7 or the 9 would both be okay. Would both be okay. So for my weak acid, strong base, I could use methyl red. I could use methyl red. Well, what about my weak base? Strong acid. Okay, that one's clear up here. All right, it's turning down here in the acid range. So I don't want to use phenolphthalein. The bromothymol blue is questionable, but this one, the okay, I said that completely wrong. The methyl red cannot be used. Sorry for my weak acid. That's the one that's bad. So phenolphthalein or bromothymol blue. Methyl red would be nice for my weak base strong acid. And then that begs the question, what about my strongies? The pH between a strong acid and a strong base is always 7 because it's pure water. When they have neutralized each other, it's pure water. So either of these two would work. Because I started acidic, so I don't want to start with something acidic, but either of these two will be appropriate for a strong acid, strong base. And that's how you would pick your different indicators. So all of those indicators that we have in the lab, we can look up their KAs and therefore their pKas, and we can judge where would you be a good indicator for. So like the Congo red and the alizarin yellow, they each have a power and they have that range. The one that we use most often in lab though is phenolphthalein and methyl red. Okay, we use phenolphthalein for our weak acid titrations, and we use methyl red for our weak base titrations. The problem with that is it's hard to distinguish where does yellow and red and orange kind of, change. So that one's kind of hard to see, but the phenolphthalein is beautiful, and you can always tell the difference. All right. Whew. Let me see, looking at the time. You guys' brains probably need a break. All right, we have done this one. We have done this one. And let me see. So the only one that we haven't done is this one. And because it's strong, it doesn't take very long. So let's chunk this one out and then we'll do a assessment. All right, so in the titration of 50 mils of 0.1 molar HCl with 0.1 molar sodium hydroxide, all right, there are not 3 equations, okay? You're never buffered. You're never buffered. At the beginning, okay, your initial, it's just strong acid. Inside, it's just acids plus hydroxides making water. And when you're done, it's just hydroxides. Okay? All right. So what is the initial pH? Well, the initial pH is just the negative log of the concentration because this is a strong acid. So it's just a nice pH of 1. Nice pH of 1. How many milliliters of sodium hydroxide are needed to reach the end point? Well, I need the exact same number of moles because this is a 1-to-1 relationship For every proton, I need a hydroxide. And in this case, they're 1-to-1. So I know that is 50 milliliters. But how many moles is that? So convert out, and it should be 0.00500 moles. What species are present at the end point? Well, when I'm done, it should just be protons, hydroxides, not from the strongs. Water, sodiums, and chlorides. Okay. All right. What is the pH when 49.9 milliliters has been added? Well, what is the equation inside the titration? It's protons plus hydroxides. So 0.00500 minus 0.004990. Do I have enough acid to sop up all the base? Yes.
4 zeros for the answer.
1, 2, 3, 4, 1.
Yep.
All right. Well, this is just excess strong. Convert it back into a molarity and take the negative log. And let me see, I had 50 and I added 49.9. Oh, look, 99.9. So my molarity right now is
1.00 times 10 to the negative 4.
so my pH is 4. All right, now here's the interesting one. What happens when you've added exactly enough? Well, what is exactly enough? Well, how many moles of the acid did you start with? 0.005. So how many moles of base would you have to add? 0.005. That just happens to be 50 milliliters. Okay, here's the beauty. Here's the beauty. Do you have enough to sop it up? Yes, I have exactly. And look, I don't care about the water, so I really have a concentration of 0. Well, you're not going to take the negative log of 0. We have water. Water will do what? And what is the pH of just water?
14.
Thank you. So together, and it's 7. So anytime you do a titration with a strong and a strong, your endpoint is always 7. Always 7, because the only thing left is pure water. And I'm not really keeping track of sig figs here very well. All right. So I've done 49.9. I've done the endpoint. Okay, so E was the endpoint. Well, what happens if I overshoot by 0.1 or I overshoot by a whole milliliter? All right, we're back to that same question. All right, so we're doing F. 0.00510. Hey, do you have enough acid to sop up all that base? No.
Are we doing F or are we doing G?
Let me see. F.
It's 501.
Oh, 501. Thank you. I don't have enough acid. But I do have a little extra leftover base. and it's a strong base, so I just need to take the negative log of it. So I need to get back into molarity. So I had my original 50 plus 50.1, so 100.1, so 0.1001. All right, and what does that turn out to be?
That's 1 times 10 to the negative 6.
And now remember, we're going to take, this is an OH, so this is a POH. So take the negative log of it.
Out.
Roughly 6. All right, so the pH is equal to 8. And for the very last one, what if I overshoot by a whole milliliter? All right, this time I've added 0.00510. Do you have enough acid? No. Oh, look, you have excess moles, and your original volume was 50 and you added 51. So your final volume is 101 and its molarity is
9.90 times 10 to the negative 1.
and take the negative log.
Calculator says 3.
And then so the pH is 11. So it's similar, but there's no buffered. Okay, it's basically just strongies and strongies. And so your graph will always turn out to look like that. Okay, or if it was a weak, or if it was a strong base with a strong acid, but they're perfectly symmetrical. There's no buffered. Okay, no buffers. And they always end at 7. They always end at 7. All right. So Kendra has to run to class. So let's take a 10-minute break, but then I will come back and we're actually going to do some of the lab problems. So Heather and Kendra, I have your midterm sitting right here. I guess I will have to email it to you. The midterm, it would be awesome to get it to me by the end of the week, but whenever you can, bye. And you don't even have to do the midterm if you don't want to. Exam 3 is over in the testing center. The midterm, most of you, I gave you a hard copy. I will send Heather and Kendra one. And again, it'd be nice to have that by the end of the week, but I just entered your midterm grades with whatever I had in my grade book. All right, so take a break, and 1:15, I'll just pause this Zoom meeting if you want to leave it going in the classroom, and I will pop back on at 11:15 and we'll just work through some of those lab problems. And it will be recorded, so anybody who wants to see it later can also watch it later. Okay, see you in a few minutes.
Thanks.